With my PhD student, Chanuri, and today I'm going to talk about the fair and optimal power allocations in a two-hop relay network for QoS support, and I will explain what is the relay network and what is the quality QoS. Actually, this means the quality of service. Okay, I will talk about later. And this slide shows the outline of my presentation. First, I would like to introduce what is the wireless network and what is the wireless relay network. And then I will provide the problem statement that I would like to solve. And I also give you the motivation of my study. Then I will mathematically model the system, and then I will analyze the system. And some numerical results are provided to show the performance of the system. And then I will conclude my talk. Okay. So this slide shows a traditional wireless network where we have a base station and a mobile station, and the base station transmits signal to the mobile station. However, so as you can see here, the signal strength at the mobile station is changed in time. Okay, and this effect is called the fading effect in the wireless network. So due to this fading effect, actually the communications between the base station and the mobile station are not always successful. Okay? So is there any good way of having more successful transmissions and communications between the base stations and the mobile station? Okay? That is our main research object. Okay? And one solution is to consider cooperative communication. Okay? Then what is the cooperative communication? Okay? So in this cooperative communication, we introduce some relay nodes. Okay? That is positioned between the base station and the mobile station. Okay? And these relay nodes forward the signal from the base station to the mobile station. Okay? And so if we have two relay nodes between the base station and the mobile station, then the mobile station have two signals. Actually here, the light green signal and the green signal. Okay? Then the mobile station can select, the mobile station select the best signal at each time. For example, if we consider at this time point, okay, then at this time point we have this signal and this signal. Okay? But you know, okay, this signal is, the strength of this signal is better than that of this one. Okay, so the mobile station take this signal at this moment. Okay, then so by doing this, we can increase the network capacity because the capacity depends on the signal strength. Okay, and this is called the cooperative diversity effect. Okay, so if we have more relay nodes, then we have the cooperative diversity effect increases, so that we can have higher network capacity. Okay, and we have another benefit by introducing the relay node in the network. Actually, this figure shows the other benefit. Actually, here, if the mobile station is very far away from the base station, then the signal from the base station cannot reach the mobile station directly. Okay? And so if we introduce the relay node between them, then you know the mobile station can receive the signal from the base station with the help of the relay node. And so this is the transmission coverage extension. Okay? So due to these benefits, so recently a wireless relay network has been widely studied. Okay? And actually this study we will consider a wireless relay network. That means a network with the relay node. Okay. Okay, next we will, in our analysis, we will consider the channel capacity, and this study is based on the so-called channel capacity. And in this channel capacity, actually its formula is given in here. Okay, we will to consider the capacity, we should consider three factors. Okay, So the first one is the source transmission power that is used by the base station. And the second factor is the channel gain. Okay? Actually, this channel gain depends on many factors, but mainly depends on the distance between the base station and the mobile station. Okay? And then we also have noise involved in communication. Okay? So, and these factors are affected. These factors affected the capacity of the wireless communication channel, and this is actually the so-called channel capacity. Okay, so if the channel gain is high, then the capacity is we have high capacity, channel capacity. Okay, now I would like to explain the system in this study. We have a wireless relay network with a single source and a single destination and n relay nodes, and we consider a decode and forward protocol in the network. Okay, that means this protocol means actually we consider a single unit time, single slot. Okay, actually the single slot is the unit time in communication. So this is a single slot, and this single slot is divided into two parts. Okay, the first part, in the first part, the source transmits each signal to the relay node. Okay, then some relay node can successfully decode the signal from the the source. Okay, but some others cannot. Okay, and in the second part of the slot, the network considers the relay node who can successfully decode the signal from the base station. Okay, and the network selects one of them. Okay, based on the relay selection strategy that I will explain later. And then the selected relay node transmit the signal, forward the signal, and actually the selected relay node re-encode the signal from the base station, and it forwards the signal to the destination node. Okay. Okay. So in this cooperative communication, we should consider two types of channels. The first type is here. Okay, the source and the channel between the source and the relay node. And the other one is the channel between the relay node and the destination node. Okay, and we assume that all these channels, and actually this channel is called the SR channels, and these channels are called the RD channels. Okay, and these channels are, we assume that these channels are subject to the Rayleigh clock fading model that is widely used in the analysis of the wireless communication network. Okay, so this is the problem statement that I would like to solve. Okay, so, as I mentioned before, to increase the network capacity, we usually select the relay node with higher channel gain. So we record the channel capacity. So if the channel gain is high, then we have higher capacity. Okay, but if the relay node with higher channel gains are more frequently used, then it consumes its power more. So we have unfairness in power consumption among relay nodes. Okay, and that results in that actually their lifetimes are shorter than other relay nodes. Okay, and then as I mentioned before, the cooperative diversity effect decreases. Okay, so in this study, I would like to solve this unfairness problem. That means I would like to find out a good way with which we can allocate the power consumption among relay nodes in a fair way. Okay, this slide shows the proposed scheme in this study. Actually, this scheme is based on thresholds. Okay? And for each relay node, we assign a threshold value for the channel gain, and this threshold value is denoted by gamma I. Okay, and from our assumption on the channel model, the channel gains are random exponential random variables with respective average here, omega si and omega id. Okay, and then so we first consider the normalized channel gain that is defined by the channel gain divided by its average. Actually, in this relay selection scheme, actually, I have to go back to my previous slide. Actually, at this moment, we should select one of the relay nodes in the network. Okay, so the channel gains GIs are involved in this relay selection scheme. Okay, so we consider the normalized channel gain and we compare this value with the given threshold. Okay, and we consider the relay nodes whose normalized gain is greater than the given threshold value. Okay, and we take the maximum of the normalized channel gain, and we denote the index of the relay node by I star. Okay. Then, if gamma I, the threshold value is higher, then relay node I is less frequently selected and hence average power. So that means, if we control the threshold values in this scheme, we can have a fair power allocation result. Okay. So the main question in this study is actually how to select the threshold for fair power consumption among relay nodes. Okay, that is our main question, and I would like to solve the question in this study. Okay, so to solve that problem, we should consider two main requirements. The first one is related with the quality of service guarantee. That means, the transmission rate between the source and the destination should be at least R bit per symbol. Okay, and for that, actually, we have two transmission and forwarding. So we have two equations. Okay, this inequality related with this transmission, and this equality related with this forwarding. And in this study, we assume that the selected relay node adapt its power. Okay, so that this equality is always hold. Okay. And the other requirement in this study is related with the outage probability requirement, and that is denoted by Wishbone outage. Okay, and the outage means outage event means the communication between the source node and the destination node is not successful, and this event occurs when all the channels are severely bad. Okay, so we compute that probability later. Okay, now this slide shows the proposed protocol that can be implemented in the wireless relay network. Okay, so this protocol is divided into 3 phases. Okay, and in the first phase, as I mentioned before, the source transmits its signals. Okay. And then in the second phase, the network select one of the relay nodes, and based on their threshold values, and in the last phase, the selected relay node transmit its power, so adapt its power to forward the signal from the base station. Okay, then based on the proposed scheme. Protocol, we can compute the average power consumption. Okay? Actually, GI, this function is the probability density function of the normalized channel gain for relay node I. Okay? And this probability is the conditional probability that the relay node I is selected by the network, given that its normalized gain is equal to X. Okay. Then, and the integral range is from gamma I to infinity, because if the normalized channel gain of relay node I is less than gamma I, then it is not contained in the candidate set. in the relay selection. Okay, then here this slide shows the outage probability that I mentioned. Okay, but I think I would like to skip the details. Okay. Anyway, so here is the optimization problem that I would like to solve. Okay, so actually this one is the sum of total the power consumption of all relay nodes, and we have two constraints. And the first one is related with the outage probability requirement, and the second one is related with the fair power allocation or consumption. Okay, and to solve this problem, okay, we first need to consider the feasibility condition, and this feasibility condition is given in this way, and this one actually, and note that this feasibility condition depends on the average channel gain. Okay? And under this feasibility condition, we should solve this problem to get the optimal set of threshold values. Okay, for that we have to analyze the system, and we first have 4 lemmas. Okay, so lemma 1, lemma 2, and lemma 3 and lemma 4, and these lemmas, I would like to skip the details, but these lemmas show the relationship between the average power consumption and the threshold values. Okay, and with the help of these lemmas, we can prove our first theorem, and that shows that actually suppose that there exists a threshold set that satisfies the fair power consumption constraint. And we also have another set that also satisfies the fair power allocation constraints. Okay? And if one of the threshold values satisfy this inequality, then all the other threshold values satisfy the same relationship, and the corresponding power satisfy this inequality, and the outage probability satisfy this inequality. Okay? Yeah, so
the thresholds depends upon the GID value?
No, threshold is priorly given. And actually the channel gain is a random variable that depends on, that it changes in time. Okay? Yes, and the distribution is exponential distribution. Okay? Okay? And from this theorem, we can prove our next theorem. Okay? This is the uniqueness of the optimal solution. Okay, so suppose that there exists a set of threshold values that satisfies the fair power allocation constraint, and this set also satisfies this equality. Okay, then we can show that actually this set is in fact the optimal set in our optimization problem, and it is unique. Okay, and so actually the sketch of this theorem is like this. Actually we use the theorem 1 in this proof. Okay, so that is, for example, if we have a set that satisfies this inequality, then by applying theorem 1, we can show that the corresponding power is greater than this, the power consumption corresponding to this set. Okay, but recall that our optimization problem is to minimize the total power consumption, so that this cannot be the optimal solution. And if we have a set that satisfies this equality, then maybe by applying theorem 1, if one element is different from that the corresponding element in this set, then by applying theorem 1, we can show that the resulting outage probability is less than this one or greater than this one. Okay, so this both are contradiction. Okay, so by doing that, we can show that if this set satisfies this one, then this set is the optimal set and it is unique. Okay?
Is it in the last two inequalities?
Yeah, this one.
Yeah, the power outage may be larger than epsilon naught if gamma is larger than gamma.
Yeah, right. See? Okay, so you know, so for this state and this state, they also both of them satisfy the same equality. Okay, but you know, we assume that this state and this state are different. Okay, then at least one of the elements is different. Okay, yeah, so for example, gamma I is greater than gamma I prime, or the gamma I is less than gamma I prime. Okay, so but in each case we have this result, which is a contradiction to this assumption. Okay, so up here we show the uniqueness of the optimal solution, and then we need to prove the existence of the optimal solution. Okay, and this slide shows the constructive proof for that. Okay, for that actually we assume that a real number, any number delta 1 is given. Okay, then and then we all threshold values are set to the same value delta 1. Okay, and we compute the corresponding every power consumption, and we take the maximum, and we take each argument, and that is denoted by 1 with angle. Okay, and so the corresponding threshold value is set to delta 1. Okay, then from this choice we have this first inequality. Okay, then all the remaining threshold values is set to delta 2, which is less than delta 1. Okay, and we decrease the value of delta 2. Then we can show that when as delta 2 goes to 0, then the corresponding the resulting every power consumption goes to infinity. Okay, so and we also show that actually this is an integral form given in integral form. So that means this function is a continuous function of delta 2. Okay, so that means so with these two properties, by applying the intermediate value theorem, we can we see that there exists some value delta 2i. Okay, that satisfies this equality. Okay. And we take the argument max of delta 2i's, okay, that is denoted by 2 with angles, okay. And the corresponding threshold values is set to delta 2, 2. Okay. And we apply this method recursively until we can find out all the threshold values. Okay. And that is our constructive proof for the existence of the threshold value, and actually we prove this. Okay, so there is, and actually that, and in this proof, then means once delta 1 is given, then we can find out, we can determine the corresponding threshold values. Okay, all the threshold values. Okay, so if we increase delta 1, then we have another threshold values, all the threshold values. Okay, that corresponding to they correspond to delta, the new delta 1. Okay. Okay. So by changing delta 1, we can find out a set of threshold that satisfies this condition and this condition. Okay. 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 So that is actually the detailed proof is given here, but I would like to skip. Okay. Okay, so here, for the comparison purpose, we consider another scheme that was already proposed in another paper, actually this paper. Okay. And in this paper, actually in our scheme, we consider different threshold values for different relay nodes. But in this scheme, they consider only one threshold value for all relay nodes. Okay, so the optimization problem for this scheme is given in this way, and with the similar argument that is used in our proof, we can also show that for this scheme there exists an optimal and unique solution. Okay, and okay. Okay, so now I will provide some numerical results. Okay, in this numerical study, we assume that there are 5 relay nodes. Okay, and these are the source power the source power, and this is noise in the communication channel. Okay, and these are so omega xi is the average channel gain between the source and relay nodes, and this is the average channel gain between the relay node and the destination. Okay, okay, the x-axis denotes the index of relay nodes. Okay, and the y-axis denotes the average power consumption. Okay, and the red line shows the average power consumption for our scheme, and the blue line shows the average power consumption for the equal threshold scheme that was introduced in the previous slide. Okay, and as you can see here, okay, so if we use our scheme, then the average power consumption for all the relay nodes are the same. Okay, but if we use the equal threshold scheme, then all relay nodes have different power consumption. Okay, so for this scheme, we have unfairness among relay nodes. Okay, and this slide actually, this figure shows the average power consumption of the network. Actually, the sum of average power consumption of all relay nodes. Okay, and as you can see here, so our scheme use less power than the other scheme. Okay, and this figure shows the average network lifetime, and you can see here. So because our scheme consume less power, so the network lifetime should be longer. Okay, and so and this result is shown in this figure. Okay, okay, and that is my conclusion. Why go too fast? Yeah, okay, yeah. Okay, we consider a wire relay network, and in this study we consider 2 requirements: the data rate requirement and the outage probability requirement. Okay, and we propose a fair power allocation scheme that minimizes the average power consumption of the network, and we provide a rigorous proof for the uniqueness and the existence of the optimal solution of our optimization problem, and we provide some comparison studies and numerical studies to show that our method outperforms. Okay? So that's all for today.
Any questions or comments